So now let's go back to a little bit more detailed view of what makes a data acquisition system work. Okay, so we've got strain gauges and a Wheatstone bridge, and now we need a data acquisition system because, well, number one, the sensor requires an accurate voltage source, an excitation source. Number two, its output is too small to record without a special amplifier. And number three, we have to properly filter and condition the signals to get good data. So the typical modern system, again, has everything, the sensor interface and the signal conversion in one package. But if we take a little bit greater detail look at it, these things all operate under software control, and we need to maybe make some excitation settings. Most data acquisition systems will allow you to pick voltages. And so we have to set the excitation voltage. The software has to decide what kind of amplification the signal needs. We have to remove the natural offset. All transducers have an offset from 0. And if you look at a cal sheet, it'll often say the ZMO. That stands for zero measured offset. Nothing, well, the first thing you'll find in the sensor world is nothing's perfect. And so I've got an accelerometer with 0 Gs. It doesn't put out 0 volts. It might put out 12.6 millivolts, which might be the equivalent of 30 or 40 Gs if I'm not careful. So we have to remove that. We have to set the hardware filters appropriate for the test and the sampling. We have sampling parameters. This is things like how fast am I going to collect data points from the sensor? How long am I going to do that? And how am I going to time align it or trigger it? Now, lucky for us in the 21st century, today most systems, ours included, have firmware that runs inside. And if you put the right setup information into the software, it figures out most of this stuff for you. But it's important you kind of know what's going on under the hood, especially if you're using these systems and then you ultimately need to understand the diagnostic information they provide. Speaking of diagnostic information, most systems today have all sorts of checking devices in place. I'll call it back in the old days, 1980-ish, we didn't have all this cool stuff that was automated. But today, we have an excitation source. But we also have a little A to D converter that's dedicated to checking that the excitation source is working. We have a shunt check circuit. We have what we call closed loop gain checking, where we actually insert known voltages into the amplifier and say, hey, I think I'm set to a gain of 160. I'm going to put a voltage in and see if you amplify me around 160 times. We have shunt checks, and we even have electronic ID. The world is going more and more toward embedding silicon, what we call silicon serial numbers, sometimes called EIDs or electronic IDs, into the sensors so that you plug them in and it self-identifies. So once you do all the basic setups, do your empirical checks, now all you do is plug them in, the thing identifies and uses the right data. So lots of diagnostics. You'll see later if you're interested and you come to one of the tables where we've got DAS working out there, you'll see the diagnostic information and and how it maybe even how it fails and what you need to do to sort out problems. On the system that's run here, I'm not going to go through all the details because I want to keep this brief. But on the system here at CAMI, we run seven tests on every channel every time they run a test. And we measure the basic noise levels. We do excitation voltage checks, sensor offset. This is the natural offset. Is it what's expected? We check the gain, the zeroing. What we call the signal to noise ratio. This means, how big is my data expected to be in relation to the noise that's in the system? Because setup errors can make that go screwy. And then the shunt check tolerances. So 7 tests on every channel every time. That's how you avoid collecting bad data. Let's talk briefly about filtering. After we get past what we call the analog front end and then apply gain, we have what's called the anti-alias filter. Now, An alias filter in this application in all of the impact world is basically what we call a low-pass filter. So if you're a signal at a low frequency, you come through the filter just fine. The scale here is frequency on the bottom and what we call the gain on the bottom displayed in decibels. And that's just a logarithmic way for talking about gain that makes it easier to plot. So 0 means that the signal comes through unchanged. Basically no change to the signal. And then at some point we have what's called a cutoff point or a knee frequency where we start to reduce the gain on signals that are above that frequency. What that does is it just isolates what we call the frequency range of interest. This is very important because in impact testing that's governed by SAJ 211, that's very clearly specified. Filters have basically 3 main properties. They have what's called a corner frequency or a knee frequency. We've got the order of the filter, which is simply what's the slope of the cutoff, and then the phase delay. All filters shift signals in time. And all this stuff is important, and it's all governed by SAJ 211. So why do I need this filter? Well, in order to understand that, we have to take a quick snapshot at what the sampling process does.